Topics for session 3. What we're going to do tonight is I'm issuing you with the assignment tonight. You'll be well pleased for that, right? And to start, first thing we're going to do, we looked at induction motors last week, so we're going to have a look at a little bit about speed control of induction motors this week, just to give you a flavour of that for your research for the assignment. Okay. Introduction to the requirements for the assignment, so we'll have a quick talk through what the assignment's asking you to do, and then we'll pick up with the theory side of things where we left off last week. So I've just inserted the slides for power factor correction into here because we didn't get to that bit, so we'll do that first, and then we'll pick up on these other techniques. So power calculations where we got a multiple load center, so looking at where you might have a distribution system and you've got a number of different loads all connected to it, how you can deal with the overall power being taken on that system. Okay, solving circuits using the power triangle, and a bit more about power and complex notation, which we started on last week. Okay, so that's the plan for the rest of this evening. See how far we get with that. Right, so speed control of induction motors. Popular way to achieve this is with using AC adjustable speed drives, commonly known as inverters. So if you've got anything to do with electrical and motors, you'll have heard of inverters. Devices available for around 20 years, suit a wide range of applications from single motor pumps, fans and compressors to sophisticated multi-drive systems. They operate by changing the frequency. You saw last week how the synchronous speed of the motor, or the speed of a asynchronous motor, if it's got some slip, is dependent upon the frequency of the supply or the number of poles. So it seems quite obvious that if we can change the frequency of the AC voltage waveform going to the motor, we can make at least an attempt to change the speed. Okay, fairly expensive, right? But they provide a high degree of control, and in many cases reduce the energy used to offset some of the extra cost. They allow for precise control of a standard induction motor by making them suitable for retrofitting as well as for new installations. So in terms of where I used to work, we also have some really complex motors to get a smooth speed control over a range rather than in steps like you'd get with a gearbox. For running the extruder on a blow molder machine, right? So the extruder pushes the plastic through the machine, makes a tube, which is turned into a plastic bottle. These motors had brushes in both ends. They had slip ring brushes one end, and they had a complicated set of commutator brushes that used to move. One set of brush rings used to go one way, one the other. And as you moved these brushes, the motor changed speed. And I've done no end of research trying to find out the theory how that motor worked, and I've not been able to find anything concrete. They were German made, but we had a lot of trouble because all the brush carbon used to get inside them and end up like shorting out between the brushes, and we'd have no end of trouble. Rewinds would cost about 2,000 or 3,000 quid. But in the end, we ended up going through a program on 2 or 3 machines. We'd done a bit of a trial, and we replaced those motors with a big induction motor and an inverter, and they were sweet as a nut. I never had a single bit of trouble with them. So they're good retrofit for certain applications like that, and they give you a constantly variable speed between limits. There are obviously limits, but we'll talk about that. But they are a good replacement for an old style speed controlled motor system. Okay. So the adjustable speed drive can be thought of as an electrical control device. It changes the operation speed of a motor. ISDs, I'm going to shorten them to that, are available to vary the operating speed of a motor by changing its frequency. Now, you guys that are on this course, and me, in my experience, we're users of motors, and we're users of speed controls. We're not designers of. So I ain't going to try and teach you the the ins and outs, the internal workings of an ASD, because you're not going to be any way interested in that and not going to be involved in it. But you need to kind of know what the pitfalls with them are and what the advantages and disadvantages are. So that's what we're going to talk about. If we ignore slip, the speed of induction motors reliant upon the frequency of the supply, and therefore if we change the frequency up, that'll go faster, put it down, that'll go slower. That's the simple theory. Okay. An inverter. The easiest description I've thought of for an inverter is it takes an AC waveform, usually three-phase, but it could be single-phase. What the single-phase ones will allow you to do, small inverters, allow you to plug in an inverter into a 13-amp socket or a single-phase supply and run a three-phase motor off a single-phase supply. You have to have a dual wound one so you can actually connect it in delta and get the right voltage to the windings, but you can run a three-phase motor off a single-phase supply, which is pretty handy if you want to run a lathe in your garage or something. Okay, so what it does in essence is it rectifies the main supply to DC. So inside there's a rectification circuit and some big capacitors to smooth it. Okay, and then it uses a microprocessor to recreate the sine waves, three-phase sine waves, synthesize them. So 3 versions of that, and because it's creating that electronically using the microprocessor, it can do all sorts of things with it. Namely, and most importantly, it can change the frequency. Yep. So that's what it is. It takes AC, it turns it into DC, and then it turns it back into a variable frequency AC. Right, there's lots and lots of complicated electronics that I haven't got a clue how it works, and I ain't interested. All I'm interested in is what they can do for me and what could go wrong. Yeah? So that's the basis of that. So let's have a look. Power and torque. Inverters actually control both the frequency and the voltage simultaneously to maintain a constant voltage over hertz ratio, a voltage to frequency ratio. This allows the motor to draw full current at any speed and produce full torque as motor speed changes. So, because if the current was different, you'd get less torque as you ran slower, which you don't want. Okay. What happens to the power when we lower the speed and torque using frequency? Okay. There's a formula there for power. It's torque times the angular frequency, or RPM, over that figure, constant 9549. If we reduce the speed, we reduce the power drawn from the supply, because everything else there is constant. If we're just simply keeping the torque constant, the number underneath is a constant. So therefore, if we reduce the revolutions per minute, it'll reduce the power we draw from the supply. So therefore, it's going to use less energy, it'll cost less to run. Yeah. So if you've got a system where you're running a pump to a tank, and that keep turning off and on, you may use less energy if it ran at a constant speed, or a controlled speed to feed the tank and keep a level. You might save energy. One way to think of it. Alright. What about increasing speed? So normally these motors run at 50 Hertz. What about increasing it? Well, some specifically designed motors can operate at higher than normal speeds, and I have seen people put these inverters, these little single phase ones, on conveyors up to 100 Hertz and run the damn things double speed. Okay. However, there's 2 primary concerns in running over speed. One was the motor or load it drives designed to operate at higher than normal speeds, i.e. frequencies over 60 Hertz. So is the mechanics of the machinery you're driving with that motor, the pump or whatever, able to take the higher speed? And secondly, inverters are not capable of increasing voltage, so at frequencies above design, the torque produced will start to reduce. But you won't keep this constant ratio per hertz torque. So torque will reduce as you speed it up. So how you get a constant torque at lower speeds, when you go above the design frequency, you start to lose torque because it can't increase the voltage above what you're putting in the first place. Yep. Even though these single phase inverters create a 3-phase output, that's a 240 volt 3-phase output, not a 400 volt. And that's why you need the motor windings to be what they are, so that they'll operate at that voltage. Okay? So that's a couple of points about, yes, you could speed motors up beyond what you would normally do with inverters, but that's something that you'd need to think about very carefully before doing it. And was the equipment designed to do that? Yeah, I mean, you I don't know, but I would think most motors and pumps are going to be designed to operate at either 50 or 60 because they're worldwide standards. 50 in this country, most of Europe 60, Japan 60, the States are 60. So, and the notes I had there were suggesting that there's no problem in going to 60. But if you've got a 50 hertz supply and you go to 60, you are going to start losing some voltage because you can't get more out than you're putting in. So you're going to drop a little bit of torque. That would be, I mean, I'm not an expert in the field, but I would think in most circumstances you're going to be okay to go at 60 hertz, even if your input supply is 50. But beyond that, you're moving into risky territory, particularly if your load is big, I would think, because your torque is going to start to drop. How are you going to then move your load properly? Okay? So inverters have a number of advantages and disadvantages compared to other types of variable speed drive. Some of the advantages are the energy savings we've already talked about. You get improved control over the process, so you can actually get your process under control. So instead of turning things off and on, you can actually have them run at a suitable controlled speed for the process. The starting voltage is reduced. There's lower system maintenance. They've got bypass capability, and I'll talk a bit more about that in a minute. And you can get versions where they can control multiple motors. Some of the disadvantages are the initial cost of buying the inverter, motor heating at low speeds. Again, we'll talk a little bit about that in a minute. Maintenance, in terms of the extra maintenance on the inverter, although in my experience they don't go wrong very often. Output harmonics, we'll talk about that as well, and the induced power line harmonics that could happen from them, and you have to be careful with. So, energy savings can save significant amounts of energy in process operations compared to traditional control because of this drawing less power if you reduce the speed. Okay. Among the most efficient types of speed control, and they're used on axial or variable torque loads like centrifugal fans, pumps, and compressors. So if you want something, a pump, to give you a variable flow rate or a controlled flow rate, this type of drive is a good way to do that because they're particularly good with that type of load. Okay. As the motor reduces the operating speed of the fan, pump, compressor, horsepower required to operate the system is greatly reduced. So you're reducing the amount of energy you need to do what you're trying to do by having one of these drives. There's a major advantage of the ASD and one of the primary reasons why they're popular. Okay. Yeah, VSDs, ASDs, they're just mnemonics. Different companies will probably use a different one. Personally, I prefer to just call them inverters because that's what they are. That's what I know them as anyway. So, variable torque loads. Variable torque loads require much lower torque at low speeds than at high speeds. The torque required varies as the square of the speed, and the power required varies as the cube of the speed. When the speed of a variable torque load is reduced to 50%, the torque required to drive the load is reduced to 25%, and the horsepower reduced to 12.5 of the amount required to drive the load at full speed. So, variable torque loads include most centrifugal and axial pumps, fans and blowers, and many mixers. So this is a situation as to why these are good for this, because you're going to get this big energy saving by using them. Instead of running something faster than it needs to, just to make sure you keep things going, you can actually control the speed of it and save energy. Yeah? And electrically, in my experience, they are really reliable. Constant torque loads require the same amount of torque at low speeds as high. So the torque remains constant throughout speed range. Power increases and decreases in direct proportion to the change in speed. So if the speed drops to 50%, the power required to drive the operation will drop to 50%, whilst the torque remains constant. Constant torque loads include most conveyors, positive displacement and reciprocating pumps and compressors. Yeah. So again, you're reducing the amount of torque required, there's less power required, so your inverter is going to use less energy because it's going to drop the voltage down and draw less power from the mains. Reduced voltage starting. An ASD acts like a reduced voltage starter to limit the amount of inrush current when the motor starts. You've all probably seen when you start up a big motor and it's got an ammeter on it, the ammeter wings right over to the ends, almost you think it's going to bend the needle, and then comes back and levels off at running current. Okay? The ASD can generally limit the inrush current to a maximum of 150% of full load current. Advantages. Improved process control. The ASD is a solid-state electronic device which lends itself well to automated process networks. It can take process signal inputs, so it can take information from about how fast the motor is running, feed that back in a loop, and actually hold that speed even when you vary the load. So you vary the load, tendency for the motor to slow down, so the sensor senses the motor has slowed down, tells the inverter, and the inverter puts more energy in to speed it back up again. So you get in a system of control. Okay? Take process control signals for start-stop, speed control from a PLC. It could take a signal to say how fast you want this system to run, and so on. Other types of variable speed control can be limited as to their interfacing with process control systems. But these inverters or ISDs are particularly good for this. Bypass capability. Okay, many ISDs make use of a bypass starter in parallel with the drive. So if you want to do maintenance on the drive, you can actually have a starter alongside that will bypass it. So you can bypass the ISD, so you go direct online, do maintenance on or replace even the ISD drive, and keep the motor and plant running. Because they're there's no other change, you're just putting the they can't be bypassed. The other systems aren't so easily bypassed as these. Another advantage, multi-motor control, so you can buy versions that will control multiple motors from the same drive. So that could be an advantage where you want a one-point control for more than one motor in a system. I've never come across, I have to say, I didn't realise that you could get that kind of application, and I've never come across that. No, I've never seen it. No, nor have I. But this come from a manufacturer. I picked this up, researched it, and it's a manufacturer's detailed information about not particularly their drives, but how.
Negative points to them if they don't use them in industries like packaging and stuff like that.
Yeah, maybe there is.
Why you wouldn't use them over just having one individual.
Or maybe they're a newer thing and we just haven't experienced them yet. But yeah, maybe. I can imagine that's only a specialist application where you want two motors to run in tandem. Do they both run at the same speed or are they separately controlled? I don't know. Okay? Yeah. I don't claim to be an expert. Disadvantages. Not the best choice for all variable speed applications. Some of the drawbacks to using ASDs, which are generally advantages to using other types of controls, are as follows. Initial cost. Generally greater than other types of the variable speed control mentioned, and is a common obstacle for progress plant to install the ASD. Payback from energy saving traditionally been used to justify. However, improvements in process control are increasingly being considered, so other types of improvement. Energy saving payback is generally low for applications where the average speed requirement is near the motor's rated speed level. So if you've got a motor that's running close to synchronous speed anyway, you're not going to save much energy by adding a VSD. That's what I'm saying there. So, whereas if by doing it you're going to be able to half the speed of the motor and still get the same production out, you're going to save money. As a general rule, a payback of 2 to 3 years typically justifies the purchase of an ASD. Disadvantage, maintenance. Like many other solid-state electronic devices, they require special troubleshooting knowledge for operations and maintenance personnel. That's all very well to say that, but I don't remember very many of them going wrong. Our little single-phase ones used to go bang occasionally, but the big ones never had any trouble with them, ever needed any maintenance. Yeah, and usually that's some kind of external issue that is too much load on it. You drop the phase or something's wrong externally, in my experience. Yeah. But yes, if you're talking about the inverter's gone wrong and that's a really expensive one, you're going to have to send it away to get it repaired, is what I'm saying. You don't have to do that with a direct online starter, do you? You change it yourself. So there's the difference. And these days they've got a lot of diagnostic capability, like you say, error codes for everything. I'll tell you exactly. It's a big problem.